The solution for question number 5 for the Chaos and Dynamical Systems paper. 5 part A, we need to plot a bifurcation diagram for this Cartesian system. And for 5 part B, we want to plot a bifurcation diagram for this polar system. So for 5 part A, we have this Cartesian system. We first need to plot phase portraits. So we need to establish where the critical points are. Critical points are found by solving x dot equals y dot equals 0. You can either use MATLAB or it's quite easy to solve this by hand, and you can see that there are at most 3 critical points. So they are at 0, 0, B and C. Again, to determine the stability of these critical points, we want to look at the Jacobian matrix. So we take dp dx, dp dy, that's 0, and then dq dx and dq dy. So I will check these twice in an examination. We have 1 critical point if the modulus of mu is bigger than 1. This makes this positive. And we also have 3 critical points if the modulus of mu is less than 1. So if modulus of mu is bigger than 1, these two disappear and we only have the critical point of the origin. And if modulus of mu is less than 1, then all 3 of these critical points are present. Next, we need to work out the stability of the critical points. So we use the Jacobian. Again, we can substitute values for the critical points. So for example, when x and y are both 0, here is the Jacobian. And we can see that when, if we take the modulus of mu is less than 1, then this is a stable node, because this, if modulus of mu is less than 1, then both of these are negative, so that's stable. And if the modulus of mu is bigger than 1, then this becomes positive, so then we have a saddle point. And for B and C, both of these are saddle points if the modulus of mu is less than 1, and this one is a saddle point if modulus of mu is less than 1. Okay, so we have 3 critical points if modulus of mu is less than 1. This circle here is given by the formula mu squared plus y squared equals 1 from the y dot, because we're looking at y against mu. So the equation of this circle is mu squared plus y squared equals 1. So when mu is less than minus 1, there's 1 critical point of the origin which is unstable. When mu is between minus 1 and 1, the critical point of the origin is stable. And when mu is bigger than 1, the critical point of the origin becomes unstable again. And these are your 2 saddle points, so they're classed as unstable. So this is the bifurcation diagram for the Cartesian system. For the polar system, we've got r dot and theta dot. Theta dot is 1, means that the origin is the only critical point. We know we have a limit cycle when r is equal to 2 gamma minus 1. Now, obviously, there is no limit cycle if gamma is less than a half. And we have 1 limit cycle if gamma is bigger than a half. If r is less than, well, for gamma less than a half, we can show that r dot is always positive. So that means that the critical point of the origin is unstable. When gamma is bigger than a half, remember we have a limit cycle. And when gamma is bigger than a half, if r is between 0 and 2 gamma minus 1, then r dot is negative, so that's why this critical point of the origin is stable. And above here, so on the outside of this, r dot is positive. So we have arrows pointing down here and arrows pointing up here. So that means that the limit cycle is unstable. It might help you if you draw little phase portraits to explain this picture. So this value here is gamma is plus a half. Okay, that concludes the solutions question number 5.